Next topic is about convolution. So the term convolution means folding or mathematical operation wherein two functions, so for example, we have function x of t and h of t produces a third function y of t or an output function. So convolution is an invaluable tool to engineers because it provides a means of viewing and characterizing physical systems. So formula as the equation shows the uh, convolution of two functions. So its useful application is finding the time response function y of t of a linear circuit. So if we have a linear circuit h of t and an input and an input signal x of t, where y of t is equivalent to the convolution of h of t and x of t in time domain. So another alternative method is transforming h of t and x of t to the frequency domain or finding their Laplace transforms and then simply multiplying the two Laplace transform functions. We will have the y of s of the response. Converting the y of s to the time domain, we have the output response. So let's consider a linear time invariant circuit and assuming that x of t equal to 0 at t less than 0 and for h of t equal also to 0 at t less than 0. So we have this is our input, this is our output, output response. And our h of t is our impulse response or the impulse response of the linear circuit. So this is a linear and time invariant. So the input function x of t causes the output function y of t. So if this is linear, suppose x is multiplied by a constant k, this also causes the output response to be multiplied by the constant k. Then suppose there's a time shift of the input function a x t minus tau. It also cause this also causes a time shift of the output response ay of t minus tau. Now if our x of t equivalent to an impulse function delta of t, the output response is equivalent to h of t. how the impulse function causes h of t, or causes the output response to be equivalent to h of t. So using the linear properties, so assuming an input waveform x of t, then we have the approximation of x of t using pulses. So we have series of pulses that have equal widths, where tau I plus 1 equal to tau I plus t ah, tau delta. If you decrease the width of this pulse, we have a much more accurate approximation of x of t. We have all widths a much uh, accurate approximation. So looking at one pulse, where the area of this pulse equivalent to the width times the height. So this is equivalent to x of tau I times the width, which is delta tau. Now if you decrease the delta tau such that it approaches to 0, we have an equivalent impulse function, where the area under this impulse function is equivalent to x tau I times delta tau times the impulse function tau t minus tau I. So this means that our input waveform can be expressed as a series of impulse functions. So impulse function here, next pulse. So the input waveform can be expressed as the sum of uh, the impulses. I mean the waveform x of t can be expressed as the summation of all impulses under this waveform. Tau I. Now because this is linear, the total output response just the sum of the individual output responses of each impulse function. So we have an impulse function. This causes an output. So means that the output response is equivalent to summation of response of each impulse function. X of or as z as delta tau approaches 0, you can write this as the integral of x tau h of t minus tau delta tau evaluated from 0 to infinity. So now this is the convolution of two functions x of t and h of